think we can get started. Welcome, class and others. Um, uh, Today I'm honored to introduce Oliver for as our second guest lecturer for the robot manipulation class. Dr. Oliver Kroemer is an assistant professor at the Carnegie Mellon University Robotics Institute, where he leads the Intelligent Autonomous Manipulation Lab. You see here, there's a cool logo here. His research focuses on developing algorithms and representations to enable robots to learn versatile and robust manipulation skills. Before joining CMU, uh, Oliver was a postdoctoral researcher at the University of Southern California for 2.5 years. He received his master's and bachelor's degrees in engineering from the University of Cambridge in 2008. From 2009 to 2011, he was a PhD student at the Max Planck Institute for Intelligent Systems. He defended his PhD thesis on machine learning for robot grasping and manipulation in 2014 at UW. So with that, I hand it over to you, Oliver.
All right, thank you, Tapo, and thank you for inviting me and that lovely introduction. So hello, everybody. As Tapo mentioned, I'm Oliver Kroemer, and today I'm going to be talking about contact modes and skills, so structure manipulation tasks. So I think Tapo already covered, most of my background. I'm originally from Germany. I did travel around a lot growing up. But yeah, since, going to university, I think Tapo already covered all that. A couple of sort of logistical things to start off with. So first of all, if there's questions, please feel free to interrupt at any time. And ask your question. I'm happy to answer any questions. If you raise your hand, I'll be honest, it's a very small screen I have of the class on my screen, so I might not be able to see it. So just feel to interrupt. Another just a quick thing. So the internet has been a little bit spotty here at CMU in the last couple of weeks. I'm not sure if it's with the changing weather or something, but do let me know if there's any connection issues. I'm hoping it's not going to drop out, but just to give you a heads up, just in case. All right, so I'm very honored to be here talking to all of you. And I'll be honest, this is sort of my first guest lecture at another university. And I looked through the syllabus and I saw that Tapo's already covered lots of different really fascinating topics, a lot of different areas that you covered. And so I was kind of thinking about, what should I share with you all today? And so it's a little bit, also I realize it's the end of the semester, so it's going to start off a little bit high level, not going into any algorithms in a lot of detail, but I guess I wanted to kind of share my thoughts on how I think about manipulation and skills and sort of how we have sort of bring structure to this problem of learning manipulation skills. So for the high level motivation, in the future, we want robots that can work in lots of different environments. We want robots that can work in homes and service industries, obviously also in manufacturing and industry, logistics, but just a very wide range of different scenarios. And really the core challenge there is how do we get robots that can handle less structured environments, right? How can we get robots that can quickly adapt to new scenarios? So, if you have a robot working in the kitchen, for example, and I hope everyone can see my mouse in case I point to things, there's going to be different objects. Each of those, vegetables is going to be slightly different than other ones. So we want robots that could, generalize to different kitchens and also different tasks in those kind of kitchens. And to do that, we really think that we need robust and versatile manipulation skills. So what do we mean by robust and versatile? So for versatile, obviously it means that we need to be able to generalize to a variety of different objects and situations. So from the cooking domain, like I said, we have different kinds of vegetables. We want to cut bell peppers versus cucumbers. We want to be able to generalize across that. But it also means that we want to be able to reuse skills between different tasks, right? So we don't want to sort of learn grasping for one specific task, and then when we have a different task, so maybe now we're cooking stew on the stove, you have to relearn grasping from scratch. And so versatility really is this idea of sort of generalizing and being able to reuse skills in different situations. For robustness, there's kind of two ways of thinking about this. The first one is obviously to avoid errors. So whenever we execute a skill, we want it to be reliable in actually achieving its intended goals. And so it should avoid errors. But I think a lot of robustness, and I say this as a clumsy person myself, is also about detecting errors and being able to recover from them. So we want robots that can sort of monitor their progress and see when something unexpected has happened and be able to adapt to that. And so if we want these sort of versatile and robust skills, really what we need is some kind of modularity. So we have these sort of skills that we can reuse in different situations. And obviously sensory feedback is going to be very important for these skills. So we need the sensory feedback both to adapt the skills and also to do this monitoring during skill executions. So whenever I think about sort of robots as autonomous agents, I usually have the following picture in my head. So at the bottom here we have the robot. It's interacting with its environment, and we obviously have some sensors on the robot, which is going to provide feedback. And I like to think about sort of the different kinds of loops that we can use to effectively correct for errors, right? So let's say we're trying to bring someone a glass of water. Well, the first low-level loop is simply controlling the orientation of the glass, right? We want to hold it upright. If it tends to get slanted a little bit, we'll try to correct for that. And we can think of that as sort of this skill, this sort of controller level at the bottom. On top of that, we might have some motion planning. We might have some actual skills. So maybe, opening up a door while holding it, or, moving the glass from one location in the kitchen to another location. So kind of a pick and place skill. That's kind of, going to give us that medium sort of feedback loop, where we're again, thinking about our environment, maybe planning a trajectory to get to a certain goal state. But maybe, we also need to sort of replan. So, if we have to open up a door, maybe we need to, change the way we're going to open the door, maybe use our elbow because our hand's not free, right? And so we get a little bit more sort of adaptation there. If we go one level even further, so the purple loop here, we're now talking about symbolic or task planning, where, if we actually drop, for example, our glass of water, then a simple motion planning is not going to recover from that. We need to figure out how to clean that up and then actually be able to get a new glass of water to serve. And that's generally the highest level, I would say, of actually recovering from a skill. The outermost loop on top of that is really learning. And so learning, the idea is that if we've made a mistake, we want to be able to learn from that. And so in the future, we're also going to be avoiding that in the past. And that, that learning loop is going to influence pretty much everything that comes underneath it. And one of the reasons I love learning is because it does sort of, connect with all different areas of robotics. Right. So we have a sort of hierarchical structure, and we can generally think about, this is sort of the very coarse level. In practice, we're going to have much more sort of levels in this hierarchy, where we have different sort of high-level behaviors calling on low-level behaviors, right? So we might have a policy or a behavior to make a sandwich, and that's going to call another sequence of different actions. So maybe first behavior it needs to do is to slice a piece of cheese, and in order to do that, it's going to first have to grasp a knife, right? And so we can think of these as skills. We often refer to them as options. Raise your hands if you're familiar with the options framework. All right, so I see a couple of hands. All right, so, okay. Effectively, an option is what we refer to as a skill. And it simply means that before you execute the skill, you're going to check that certain conditions are true. And then later on, you're going to end that, that skill when some other conditions are true. And we'll talk a little bit more about options, I think, later on. But the idea is that effectively, we have these different behaviors, and we want to sequence them one after another in order to perform these high-level tasks. And this sort of hierarchy provides a lot of utility. So we obviously get reusability through this. So grasping a knife, we can use it here, but we can use it also for grasping other objects. So for placing a slice, for example, we can grasp that slice. And it makes it a lot easier for these high-level behaviors to effectively learn how to perform these more complicated tasks if we've already learned these low-level tasks, right? And so when we talk about skills, we're often talking about kind of these medium-level behaviors, right? So things like grasping, scooping, cutting, throwing. These are all kind of medium-level behaviors where we probably still have some kind of controller underneath it. We have some kind of trajectory generator, but they're not at the level of making sandwich, right? So very few of us would sort of say that there's a making a sandwich skill. There's a behavior, there's a policy, yes, but usually we wouldn't refer that as a skill unless you're very good at making sandwiches, and a master chef maybe then. So then the question is really what makes for a good skill? And there's different schools of thought on this. One approach would be to sort of say it's a repeated behavior, right? So if I'm grasping something, I'm going to be grasping other objects as well. So this is kind of a behavior that we see multiple times, and so maybe that's a good point. But repeated behaviors can be tricky. So if I move my hands up a little bit, is this now one kind of skill? Or is it multiple small ones where every little step of that is going to be its own skill, and it's just a collection of multiple skills. So another way of thinking about this problem is how do we best decompose a task such as the one shown here? So here we have a bimanual grasping task, first demonstrated with one hand placing on it, then we pull it the other, and then we lift it up, right? And I think we can all agree that if we look at this, there are going to be certain skills that we kind of expect. So for example, here we have the robot. It needs to pick up this object. It's on the right-hand side from our perspective. So first takes this hand, places the second hand, and then lifts up, right? And so you can kind of break this down into placing one of the hands on the object, picking it up, and then lifting, right? And then if we also have the object more on the other side, we can reuse some of these skills. So now we might choose the other hand to place first, and then the second one. And so, we can kind of reason about different sequences. So it doesn't really matter which hand we place on there first, as long as we sort of lift it up, right? And we can even reuse these skills so that when we place our hand on it, we don't actually have to lift it up. We may just sort of slide it more to the side, okay? And so I think, placing hands on objects, lifting them up, I think most people would agree that, these are, very useful skills that could be, used in different combinations to perform different tasks or the same task in different ways. So I would argue that, the fundamental concept that we're really using here, though, for identifying these skills is the idea of modes, all right? So here we have a picture of 4 different modes. So you can think of a mode as a sort of discrete element of your state space. And in particular, it's going to sort of identify situations where there's a different dynamics, all right? So what does that mean? So, let's look at these top pictures first, starting on the left-hand side. In this picture, in this situation, if I were to lower or raise my hand, all that would happen is I would lower and raise my hand, the object would move. Whereas in this middle one, if I try to lower and raise my hand, it would apply a force, either a force down into the ground or a lifting force, which at some point is going to lift it high enough that it breaks contact with the surface, in which case I'm in this third mode here, where now if I move my hand up and down, I don't just move my hand, but I'm also moving the object, okay? And similarly, if I try sliding left and right, at some point I'm going to get overstiction, and I can actually slide this object around. So you can think of this as another mode as well. So why is it useful to think about modes? So one reason is that it kind of decouples getting to a state and actually using that state, right? So there's different things we might want to do once we've grasped this object, but in both cases, but in general, we first need to grasp it before we can do those things. So segmenting our tasks based on these sort of mode transitions are going to decouple getting into a mode and actually using that mode to perform some additional manipulation. Another important part is that they're often sort of associated to sub-goals and error states. So in this case, we have effectively different constraints here of staying in contact with the object or lifting it up. And so if we wanted to sort of pick up the object without sort of scraping the surface, then we could say that moving to the right here, this is a sub-goal, and scraping along the surface, that's going to be an error. And so the mode switches nicely align with sort of sub-goals and errors. Of course, if we wanted to actually use this to sort of scrub the surface, then we could sort of say that this upward motion is now an error state, and the sort of moving laterally across the surface is going to be our sort of our goal state. So we want to be able to go through this sub goal, and so we can start seeing how we get this nice sort of structure of sort of sub goals and sort of bottlenecks in the state space that we need to go through in order to get from one to another. So if we want to reach this state, we need to make contact with the side. If we want to go to this mode, then we need to apply enough upward force. The last thing, I think this is very important, is that when we have a mode transition, there's also a very clear sensory signal. So in this case, when we make contact with the object, we're going to generate little vibrations, which we can detect with our fingers. If we slide it across the surface, we're going to create a scraping sound as we move. And even when we lift it up, there's little tiny vibrations created by that breaking of the contact. And so, as we sort of transition from one to another, there's also very clear indications of when that happens at the sensory level. And there's actually some great work by Johansson and Flanagan. If you haven't read it, I strongly recommend it, looking at how sort of different tactile different tactile nerves are used for something as simple as picking up an object and the different phases. So here you can see we have a reaching phase, which is that first one, loading, which corresponds to applying an upward force without moving the object. And then we're finally in the lifting phase, where it's going to be moving upwards. And down here, these are actually looking at the sort of the firing rates of different afferents. So we have slow afferents and fast afferents. Slow ones effectively can capture constant pressures or low or slowly changing pressures, whereas fast afferents are interested in these sort of very high frequency vibrations, such as the ones we get when we scrape a surface or make or break contact. All right. And as we'll see, a lot of the work that we've been doing is also very interested in this idea of using vibration signals. All right, so hopefully I've convinced you now that when we think about our skills, what we often want to do is we want to learn skills in order to sort of correspond to some of the mode changes that we see during the manipulation tasks. And so for the next part of this lecture, we're going to be focusing on thinking a little bit about if we have this sort of sequential structure of skills, how does actually sensing, in particular tactile sensing, play a different role as we go through our skill executions, right? So when we think about tactile sensing, maybe the first thing that we often think about is a very simple tactile servoing, right? So here we have a robot. It has this very large hand. There's some pressure pads on there and has a spatula. And effectively, we want it to be able to scrape the surfaces at a certain amount of force, all right? Now, if we sort of change the surface, so we make it a little bit higher, if we just blindly go down, then we're obviously going to apply more force. But by using tactile sensing, we can sort of regulate the height that we're trying to aim for. And so we get this sort of nice scraping motion despite what the height is, right? This is very similar to force control. In this case, it was learned using tactile sensing. And so we can visualize this kind of constant feedback as follows. So here we have a sequence of skills. We have our previous skill, we have our current skill, and we have a next skill. All right, and so we delineate where this current skill starts and stops. And for this kind of tactile servoing, what we often have is we take a small window from our senses, and we're going to use that to choose an action at the end of that window. And then we just repeat that. So effectively, each of these windows might be looking at what is the current force that we're just detecting on each of our taxels, and then figuring out how do we adapt our trajectory in order to make sure that we get the desired force, right? And that allows us to sort of avoid small variations in the task and still achieve the overall goal. But another way that we can use tactile sensing is actually at the beginning of our skill. And in particular, when we finish our previous skill, we're going to have to sort of select which skill we're going to choose and also initialize some of the parameters, right? And from vision, I think a lot of you can imagine what this would look like, right? So if I want to stack two blocks on another, I'll look into the scene. I'll see that I can A is in a state where I can grasp it. B is on a state where there's nothing on top of it. So it fulfills the preconditions of a pick and place. So that I can actually execute that skill. And maybe I choose the height that I place it based on the height of the second block. But what does this look like for tactile sensing? So for manipulation tasks, obviously we're often interested in tactile sensing because of the contact-based nature of it. Well, let's look at a task which we've been doing a lot in our lab, which is cutting. So here we have my student, Kevin. He's demonstrating to a robot how to do a cutting task. I should mention there is another student off camera with their hand on the emergency stop. So this is using the gravity compensation of the robot, make sure that it's all safe. And he can give some demonstrations of this behavior. So here we trained DMPs. I believe everyone's familiar with DMPs. Let's just see a quick show of hands. DMPs? Yes, okay, great. All right, and so we get this sort of DMP behavior. So we have the back and forth in the X direction. Y is sort of left and right, so there's not a lot of change. And Z is simply this sort of moving down a little bit every time. And we show this now for a cucumber, but we also want to be able to adapt to different types of food items, right? So in some cases, you might need more back and forth if it's very difficult to cut, or you might just, if it's something like tofu, you probably just want to go straight down without a lot of back and forth, which might, break it. So the question comes, how do we sort of predict what these different, amplitude, what the amplitude should be for these different kinds of trajectory? And to do that, we're going to use information from the previous skill. So in this case, the previous skill is simply moving down into contact, right? So we have this moving down, we're making contact, and we have this mode transition at the end of the skill where the knife makes contact with the object, right? Now, important thing to note in this picture, obviously there's the knife and the cucumber, but we can also see the back of the knife, this little red item here, and also the same item over here. Does anyone know what this object is? Anyone play guitar? No? Okay, it's a contact microphone. So effectively, what we can do is we can listen to vibrations in the knife as well as coming through the tongs in order to sort of capture those vibrations in order to use them for identifying different kinds of objects or events. And so in this case, what we're mainly interested in is actually recognizing what these food items are. Now, obviously, in some cases, you could use vision to clearly classify different ones, but in some cases, it's actually quite challenging, right? So for example, here, we have a orange, a lemon, and a frozen lemon, which visually are very similar. We have a cucumber, a zucchini, and an old cucumber, which are again very visually similar. And in all these cases, we're not actually using any we are using perception. We're not using any visual perception. What we do is we simply want to classify which of these objects it is based on the vibrations that we detect when we move our knife down. All right. And then for each of these objects, we at this point sort of pre-specified what the amplitude should be for both the back and forth motion and the downward motion of the DMP. Right. And so what we do is we want to be able to classify these 25 different food items. And we do that using a fairly simple network. So this is just 3 fully connected layers with 100 units each. So fairly, bread and butter. I would say that, one of the key things that we do, though, is we use the MFCC features for the vibrations. So we effectively get this 0.1 second, the final 0.1 seconds during that last motion where it's actually making contact. It's getting information about this object through this interaction. And what we do is we take the Mel frequency Cepstrom coefficients. So what is that? So the Cepstrom coefficients is the power spectrum of the power spectrum. So if you take your signal and you take the power spectrum, you're going to get a signal that tells you, what different frequencies you have more power. And the Cepstrom is effectively taking that power spectrum, treating it as another signal, and then effectively taking the power spectrum of that. All right. And the reason that's very powerful is because it helps to sort of identify different harmonic structures. So from a human intuition, we often think about this as the timbre, right? So if you have a brass instrument and a woodwind instrument playing the same note, it's going to be the same sort of frequency, but it's all about those higher level harmonics that are going to give you those very distinct sounds, right? And we're doing the same thing here, except that instead of brass and woodwind, we have broccoli and cucumber, right? Those are our instruments. And so if we actually train this classifier, we get the following confusion matrix. So this is obviously a lot smaller. That's because we're really only showing the errors here. So for example, we get, sometimes a watermelon was mixed up with a frozen lemon. So, they both have very hard outsides. Again, this is not using any vision information. This is just the force signals and the vibration signals from that initial interaction. And, we also get spaghetti squash, might be mixed up with a watermelon. Overall, we got an F1 score of 0.99. I should mention the fact that, this is a very controlled kind of situation. So, the robot's always moving a similar way down. It's a similar part of the workspace. And so, there's not going to be a huge amount of variation. I'm sure that, if your robot was, holding its hand and just randomly chopping, we probably wouldn't get this good of a result. But for this kind of scenario that we have, it actually works very well indeed. And so, if we apply this now to our system, it goes down, it detects what kind of object it is, and then it can sort of, choose the corresponding parameters for the skill, the actual cutting skill, right? And one nice thing, so this is sort of, within the classes that I was trained on, we can also look at different objects. So in this case, we're giving it a peach, and it's never come across a peach. But it sort of thinks, okay, zucchini seems very similar from a tactile sense. And if you've ever cut into sort of an unripe peach, I think you can agree those are fairly similar. Down here, it doesn't know what a pear is, but apple obviously has a very similar kind of vibrations, that nice crunchiness that it has. I think my favorite, though, is this one down here. So obviously, bell pepper is very large. Jalapeno is much smaller. Technically, looks a little bit more like a cucumber. But both of these, peppers have this nice sort of, big cell, very juicy structure to them. And so from the vibration perspective, they're actually very similar to each other. And so even though it's never come across a jalapeno, it knows to use similar parameters to it would with a bell pepper. And so in all these cases, we're using this initial information from the previous skill when we first made that mode transition in order to choose the parameters for our new skill. So another way that we can use tactile feedback, or generally feedback during a skill execution, is termination, right? And I mentioned also that we often model skills as options. So in an option, we have a policy that has a precondition, which you can think as being part of the initial, the selection or initialization. And the second part really is this termination. So we need something that tells us, now we're going to end this skill and we're going to move on to some other skill. And so you can think of it at, at every single time frame, it's going to be looking at what's just recently happened. And in most cases, it's going to say, okay, keep going with the skill, keep going with the skill, keep going with the skill, often until some kind of a contact event happens, and then, we want to stop, right? And that, that contact event, that could be, we've reached our goal, so that's great. But it could also be an error, right? So if we, for example, going back to the example of carrying a class, if suddenly, we feel a lot of slip in our hands, or, a sudden, okay, if it's slip in our hand, it probably means we've just dropped the glass. If there's a large force, maybe it means we bumped into something. Maybe a nice sort of, easing of the force from below might indicate that we actually achieved our goal of placing the glass somewhere that we want it to be. So if we think about the termination for the cutting, we have a lot of different events that we can sort of base it on. Again, we're using a lot of this idea of mode transitions. So we first have, making the contact with the top of it, but we can also detect when we start scraping with the cutting board, right? So it's going to give a very distinct sound compared to the actual vegetable. And again, we trained a very similar network. In this case, we looked at sort of things like in air, or whether we've hit the cutting board, if we've hit the object for the lowering the knife. So the cutting board, this kind of means that if it detects that, effectively meant it slipped off of the object. So sometimes we go for slices that are a little bit too thin. So when we lower it, it just kind of hits directly the cutting board. For the slicing, so while it's actually in there, it can detect when it's effectively cut. Well, in air is kind of probably unlikely, but scraping the object, slicing the object, scraping is at the top surface, slicing is when you're inside of it, and then we want to terminate when we actually get that cutting board. And so again, we can use this sort of MFCC representation and this 3-layered neural network to nicely classify these different events, so we can use them for termination. Of course, it doesn't all have to be about directly contact. So in scooping or in pouring, I should say, we also maybe need to terminate our skill at a certain position. So this is another project that we looked at, looking at sort of scooping and pouring different materials. Here we have coffee beans. We also did things like plastic pellets and pasta. Again, we use this sort of contact microphone on the back. So like I said, we're very excited about using vibration signals as our cheap sensors. And what we can do is we can effectively monitor, during the execution, listen for the amount of vibrations and try to estimate the mass that's flown out. So here we have a spectrogram. So over time, we have different amounts of frequency, and we effectively learn to predict how much sort of mass is flown out of the scoop when it's pouring at every time step, right? So we have these small little windows. These are being added up. And then, once we sort of reach the desired amount or some, lower level threshold on that, then we can terminate at that point. And here you can see what this looks like in practice. So it's sort of, gradually pouring out. And then once it's detected enough material has been poured out, it's going to stop. And here you can see on the right-hand side, the commanded mass. Obviously, we have these plastic pellets here. They're a little bit more dense than coffee, which is why we have this greater range. But we can get fairly close to the desired mass just using these vibration signals. We actually found they work better than sort of using force torque sensors for this task. So another sort of work that I want to mention. So we talked about the idea of sort of treating it as almost like a classification problem, where we're trying to, we kind of say there's different kinds of outcomes, and we're trying to classify each one of those. For the last one with the pouring, we treat it more as a regression problem. So there's a certain goal state we're trying to reach, and we're effectively predicting how close are we to that goal state. Obviously, that one wouldn't work quite as well if you had people suddenly bumping into it. The other method I want to talk about is just outlier detection. So, many cases we're going to have very stereotypical executions, especially if we do something like DMPs. And so this is a paper of Peter Pastor et al. From 2011. Is it 2021? It's been a while. And the idea here is that, rather than trying to predict all the possible different kinds of, bad things that can happen, so the different kinds of error states, if you have a very stereotypical execution, you're also often going to get very stereotypical or sort of very consistent behaviors over that execution. So for example, here, there's a PR2 trying to flip up this, this block using 2 chopsticks. And if everything goes well, we get these sort of nice green plots of the forces over time. And they're fairly closely bundled together. It's a very similar kind of behavior. There might be slight shifts, but usually the robot can handle those small changes. Whereas, if something happens bad, then we're generally going to get a larger shift away from those distributions, which are indicated by the red. And so we can simply see, when that happens, okay, we can just terminate here and switch to another behavior, right? So, this is the idea of sort of outlier detection. It assumes that actions are a little bit more stereotypical, but it can also generalize nicely to different situations. So, okay, yep, I'm sorry, that was right. So you can see Peter actually teaching a robot how to grasp an object. And he teaches a bunch of different kinds of skills, executes them under slightly different conditions to sort of get an idea of what those good sensory choices look like. And so then when it's actually at execution time, you can run it and detect when an outlier happens and then switch to another skill at that point. Right, so in this case, it kind of detect that it bumped it, right? And that's a good place to sort of terminate, because if you continue moving forward, you're just going to knock it over. In this case, humans being mean to the robot moved it to the wrong side. So again, it detects it, and you have that nice sort of error correction throughout.
So Oliver,
Yes.
Is this done independently at every time step, or is there like a Bayesian or like some belief you maintain about the state of the object, like where the state object is?
So in this work, it was effectively at every single time step.
Okay.
I should also mention, although it looks like a Gaussian process, it's not. It is just at every single time step during the DMP. So you obviously have that time synchronization with the DMP. It's just fitting a Gaussian at that time step. And that's also why you can have fairly large steps if it's fairly consistently making contact. Yeah. A good question. Thank you. All right. So with termination, the goal is really to just sort of, figure out when to stop the skill so that you don't sort of overshoot your goals, or if an error has happened, that you can, switch to a different skill as quickly as possible. The next thing I want to talk about a little bit is outcome detection. And this is really thinking about, when we've finished our skill. So, we're not looking at this at every single time step, but rather once the entire skill is over, can we now identify whether, we succeeded? Or if if an error happened, or we did succeed, what kind of success was it? What kind of error happened? And so, we can formulate this again as a kind of a classification problem. I would say that one of the benefits of this kind of a classification is that because we're executing a skill, there's a lot of context that's provided, right? So if I know that I'm grasping, if I detect sort of, the certain forces at the end of that motion, it probably means that I'm, interacting with that one object that I was trying to grasp. I don't have to sort of think about, a huge variety of different events that could happen during that grasping motion. And so, we often sort of treat this as kind of a classification where we can focus in on certain aspects of the environment without having to consider the full state space. And one area where this has been studied quite a bit is looking at grasping. So, you grasp an object, and before you sort of lift it up, you'd use your tactile sensor readings, get some features from those readings, and then pass them to a classifier to sort of say, was this a good grasp and I should pick it up? Or if it wasn't, maybe I should, let it go and try to re-grasp it before I accidentally knock it over. And yeah, so there's been a couple of different, or a lot of works in this sort of direction. So, some of the early stuff from Yasmin looked at sort of, directly looking at tactile sensor images. So these are from the Schunkhand, the different, the tactile arrays. Mariana Madri, they looked at sort of, taking more of a hierarchical approach over the time. Again, looking at these sort of sensor levels and sort of accumulating a lot of it over the entire trajectory. And I also like the work from Dang and Allen, which sort of said, let's not just give the robot the joint angles and the tactile images, but we can actually reason about where these contacts are being made in 3D space, and then effectively, classify based on that. All right. So just looking at the time a little bit. So we did actually develop our own method. This was still during my PhD days, looking at classifying different contact distributions. I'm going to go through this a little bit quickly, but the idea is effectively that we have these kernel methods, which are computing a similarity between different contacts. So we want to look at, how similar are the contacts in this situation and this one. And effectively, the way we do that is we have a model of the object, we have a model of our hand, we extract some contact points. We also have the normals with those. And then for each one of those, we fit a Gaussian distribution. So this is like a 60 Gaussian over the positions and the normals. And then once we have those Gaussians, we can actually use an off-the-shelf Bhattacharya kernel to capture how similar those distributions are. So if you have similar contacts on objects, you're going to have similar contact distributions, and therefore you would expect similar kinds of interactions. And we applied this, for example, to grasping a variety of different objects here. So we have this it was a reflex hand, which has very simple tactile sensors on there based on barometers. We kind of put these, here you can see all the different contacts in 3D space. So the palms down here, this is effectively how the fingers close. And depending on which objects you're contacting, you're going to different sets of these contacts being active. And we compared our Bhattacharya kernel to a bag of features. So I guess what I'm trying to say is that there's a variety of different sort of ways of sort of formulating this problem, of sort of predicting whether the outcome was successful or not, and using different kinds of tactile representations. Beyond sort of grasping, we can also think about things such as insertion tasks. So in this case, we want to be able to know whether we achieved a certain goal. Here we have a insertion task where it's not just going directly to the hole, but we actually have a curved groove that we want to use. And so again, if we sort of split this up according to different mode transitions, we're going to get smaller sort of sub-skills during this task. So here you can see a demonstration. And if we actually sort of segment this based on sort of the changing sensory signals, what we get is the following. So we have the first skill going down to make contact. That's obviously a nice mode transition. We have sliding into the groove. It's going to give us a very clear signal. We then have one going into the corner, one to the top of the hole, and then one finally going to the bottom. And what we can do is we can actually train a classifier, again, sort of on the vibration signals, to detect each one of these events throughout in order to classify whether we reach the goal or not. So what will often happen is we'll sort of move towards a desired location, but it won't quite reach it. Okay, so particular, we'll try moving to the groove, but we won't quite reach the groove. Or we'll try moving to the corner and we won't reach the corner. What we can do is we can use outcome detection to simply detect when these events happen and then reattempt the skill from the current location. So for example, here is a failure to reach the groove. And now if we just simply blindly continue on with the sequence, then obviously the overall task is going to fail as well, and we don't actually get into it. But if we allow the robot to do outcome detection, try to like classify when it actually reaches the groove, we get something like this, where at first, let's go back, it didn't reach the groove, it detected it didn't reach the groove, so it tried sliding again that direction. At that point, it reached the groove, it terminated earlier, and then can continue from there. And similarly, reaching the corner, if we don't reach the corner and start sliding towards the hole, in some cases, the object. But if we actually allow it to detect that it hasn't reached the corner and try again, then we can robustify the system. All right. And so, I think that's a valuable lesson that in many cases it is just a small adjustment that needs to be made in order to get something that's a lot more robust. And if we do that, then we can actually make the system overall more robust. All right. So that was looking at outcome detection. So thinking about, given the information we know from the skill, was that actually, successful or not, and what kind of an, if it was a failure, maybe what kind of failure happened. The last part that we're going to talk about is verification. And this is really thinking about not just the current skill, but the next skill, right? So if we allow the robot to perform another action, how can that actually help us to get a better estimate of the outcome of the previous? And I think this is exactly one of those cases where having skills that terminate in mode transitions is very important, because obviously when we have a mode transition, we're going to have a change in dynamics. And so we can use that next skill to actually test those dynamics. Or another way of saying that is we can use interactive perception to determine the outcome. And most of you have probably seen some examples of this. Probably the most classical one that as humans we do is, when we leave our home in the mornings, we want to make sure that the door is properly locked. We'll close the door, and then we might tug on it a little bit, right? And that sort of tugging, that's kind of our next skill. And from that, we can identify that, yes, it was actually a good closing. We did detect the click when we pushed it. That would be the outcome detection. But that additional tug, that's part of the verification. And if we think back about some of the examples we had, this is actually for the scooping and shaking project. So here we sort of scooped, and we want to estimate how much was actually in the scoop. Obviously with vibration sensors, it's difficult to kind of tell just from the actual scooping. What we can do is we can shake it afterwards. And we actually trained a network that could estimate within 5 grams of how much material was in the scoop. Another common example is lifting and shaking after grasping. So a lot of sort of self-supervised grasping methods will sort of pick up the object and shake it around to test whether it was a good, a successful grasp or not. A little lift can also help, just to get a better estimate of the force distribution. And you can actually, use this information for a learning signal, right? So ultimately, every time we pick up an object, we don't want to shake it around, but while we're learning, that's often more acceptable. And so we can, use verification as a self-supervised learning. So here, for example, this was a project we did at USC, where the robot's learning to re-grasp objects. So it picks up the object, gets an estimate of the force, and then it tries to pick it up again. In this case, it failed. It gets a reward of 0. Here we have another one. It's going to be, again, a failed grasp initially. We try to re-grasp it. And in this case, it initially seems like it's going to work. So we think it's going to be successful, but when we shake it around, it falls out. And so we'll give it ½ a point, whereas if it stayed in the hand, it would actually get a full point. All right. And so we can use these kind of additional verification behaviors in order to provide additional supervision, or in this case, reward acquisition for these skills. And here you can see the final regrasping. So picks up a little bit lower when it regrasps it, or in this case, it sort of aligns the hands nicely with the object after that first grasp. All right, so we kind of looked at different ways that we can use sensory signals, in particular tactile sensing, during these sort of skill executions. As we can kind of see, a lot of these are very much focused on the outcome of our skill, which makes sense, right? We want to make sure that our skill is doing what it's intended to do. Obviously, we need to set things up properly and control it to get to that outcome. But termination, outcome detection, verification are very much focused on providing information about the outcome. And the reason that often we have skills that sort of focus on these sort of mode transitions is because they provide a very salient goal event, right? So we're bumping into something, we're making contact, there's a lot of sort of vibrations and force changes that we're detecting. And so it becomes very easy to identify these different kinds of goal events so that we get a very robust skill if we're looking at those, right? If in contrast, we had a skill that's, moving to a point in free space, yes, we could use, visual information, but, depending on how you put your head, it's going to be, going to look different. There's lighting effects can easily change our perception of that. So there's no really strong, clear signal about when that happens. Whereas with tactile sensing and these sort of mode changes, we can get, very clear signals. The other part is the verification. So because we have switching dynamics, it allows the robots to really perform an additional action to test that outcome. And that can be very useful, as I mentioned, for sort of learning skills, because it provides us a ground truth or a way for the robot to autonomously test whether something was successful or not. And so it can, during training time, perform these additional skills, get its own the sort of label about which mode it was in, and then it can use that to effectively train things like the outcome detection, the termination conditions on its own, or even the whole skill, assuming that the goal is to get to that desired outcome. So for the salient goal events, I do want to mention another sort of line of work. This is, again, not my own, but the idea of sort of discovering skills using distinct effects. So when we think about acquiring different types of skills, one approach is obviously to have a demonstration, as we saw at the beginning, so with the two-armed demonstration, and then effectively segmenting that into different sort of skills, often based on sort of these mode switches. But even through sort of self-play, if we take this idea of sort of salient outcomes as being very useful, we can also discover skills autonomously. So what we can think about is we're going to have some kind of a controller. It's not quite a skill yet, I would say. There's no sort of preconditions that need to be suitable for when it's executed. There's no clear intended effects. It can even start off as something as general as sort of motor babbling, right? So moving your arms to different locations in different situations. And so, we can think about this as sort of some, samples where we have our states, we have our actions, and when we execute those actions, we'll get to some next states. All right. And so these could be things where, our tactile sensors were signaled, or something fell over, or nothing moved maybe. But what we're going to see is that there's often a lot of sort of similar kinds of effects that kind of cluster together. And so to create skills, what you can do is you can effectively take those different clusters, cluster them together, and then go back and effectively say, like, okay, all the situations and actions that led to this cluster, we're going to call that one skill. The ones that went to this cluster, we're going to call that different skill. And in this case, again, states and actions, we're going to map to different a skill. So in doing this, we can sort of build up this sort of very primitive kind of hierarchy of different skills. So motor babbling, where you're kind of just moving your arms around in random locations. If we move to free spaces, we can get reaching. If we start interacting with objects, we can get pushing. If it sort of knocks something over, or grasping, if it sort of holds it in our hand afterwards. And these can be further refined. So pushing, we can, depending on whether there's a lot of rotation, it can either be rolling away, it can be sliding, or just be tumbling 90 degrees. And similarly with grasping, it might end up just triggering the fingertips, or the power, or more of the hand, in which case it's a power grasp. So this is a work from Emre Uger, looking at sort of applying this kind of concept to the real world. or a real robot. So it's, it's just doing random actions, the objects in different locations, and it's effectively doing this kind of clustering to find different kinds of skills. More recent work, there's also a paper by George Konidaris looking, I think it's from skills to symbols, which is looking at a very similar idea, but a lot bigger in terms of multiple steps of a skill. So here we see the no touch example skill. So the object doesn't move. Push. So here we have the salient event that the object actually moves, and we get some tactile sensing. Carry. So in this case, it also closed its hand. And I would say a drop. They call it a release, where it actually picks it up and then releases at the end, drops at the end. All right. So
Oliver?
Yes.
How do you decide like the number of clusters?
That's a great question. So to be honest, I don't remember exactly how they chose the number of clusters. When in previous works where we've looked at sort of mode changes, one way that we've done it is looking at sort of spectral clustering. So we sort of have some kind of a similarity measure, and we use spectral clustering, and then we because with spectral clustering you effectively have like a similarity between each pair of samples for this sort of the connection between two. So okay, let me explain that a little bit better. So for example, we did, for example, clustering with objects interacting with each other. So where there's like a poke or inside of it, and we wanted to cluster that. And so we use, for example, the kernel method to sort of compare the contacts between different sets between different pairs of objects to get that sort of that kernel. So for every single pairs of objects and every other pair, we can have some kind of a similarity in the contacts. And we would apply spectral clustering, assuming different numbers of clusters, and then we would effectively score them based on how much they sort of, if the same cluster puts very similar ones together, and if it puts separate ones, in different ones, we would sort of take one minus that cluster similarity, or that kernel similarity, and then we just choose the one that has the highest score. So that kind of moves it from a problem of choosing the right number of clusters to more sort of choosing the right sort of similarities function. There's still hyperparameters, but I find those to be a little bit easier to yeah.
I have a question.
Yes.
So if you go back to the previous slide, well, actually, I don't know if it's the previous slide, but those slide with the state and actions.
Yep.
Yeah, right. So from what is shown over here, you seem to take actions that go from one state to just another state, right? Try to cluster these actions to be a skill. But what are these actions in the first? Like, what is the difference between these actions and like skills in themselves? Because from what you've described before, actually, like skills themselves are multi-time set, like sequential actions, right?
Yep. Yes. So the okay. So let me see. So I would say that this kind of comes down to this idea of options, right? So for every option, we're going to have our policy, right, which is, or just say action given state, right? This is our trajectory generator, it's our low level controller. It's the behavior, right? And the important parts that we're sort of missing are, I would say, the preconditions and the effects or termination, right? So what we're effectively providing to the robot in these kind of situations is just this middle part, right? So it's a very general purpose policy that could be, move to your arm to a different location, or drive to a certain location, or where a certain location could be various different goal states. And so the idea is that when we go from sort of that skill policy to an actual skill, it's all about finding the preconditions and sort of these effects determination conditions, right? So that kind of wraps it up into a bundle that kind of is a skill, right? So you can think about it as learning to open up a door, right? So I can do this kind of a behavior, just moving my hand, swiping at different locations in the world, and in most cases that's not going to do anything, right? It's just a pawing in the air. But now if I have something like a door there where I can put my hand on there and now the door actually moved, that's going to be a sort of a salient event, right? It's going to be a distinct kind of outcome where now the door actually moved. So that's where we get sort of, this cluster of goal states. And
so if I'm not mistaken, the action over here is more just like the different policies that you take, like the different pies that you provide, like different sorts of actions, like the pie we given us is like different sort of policies pie, right? As like
yeah, so I mean, maybe action is not the best thing to hear. Maybe it's more like the parameters of your policy. But yes, so if you imagine like another way to think about it is like, okay, let's go for like a DMP policy, right? So you could say that your weights and your goal state, those are maybe all, your parameters. And so as you have different kinds of weights, you're going to have different kinds of effects. And then by clustering those together, you can start to identify like, oh, these are, different ways of getting the same one. Now you might want to segment because, there might be different ways of achieving that with the DMPs, but you would get something like, okay, these are all at least door opening ones, right? And then based on that, you want to sort of say like, okay, what are the states and the parameters I had to choose in order to open those doors? And then that's how you discover a door opening skill.
And so does that mean that the states themselves contain information about possible conditions, like preconditions? So the S in this case, like how else do you learn the preconditions for such actions? Like
right. So the preconditions can be learned in a self-supervised manner. So that's one of the great things about preconditions is that once you've specified some kind of a distribution over the the goal, right? That kind of creates a test. So I can execute my skill in various different situations and simply see, okay, did it actually reach this desired goal state? If yes, then I was in the preconditions. If no, then I was outside of it. Right. And yeah, so personally, I'm a huge fan of preconditions because it's also like, they're really important, I think, for also sort of defining the scope of your skill. So, as we mentioned here with this sort of door opening, now we've got like a very primitive door opening task, but these skills that we're now using to open up the doors, we also have where we can actually use them, right? So it gives it like nice scope. So it means that there's no door around. I don't have to be able to execute this skill. I can simply say it's outside my preconditions. And I think that's going to be very important for robots going into the real world, having those correct preconditions to identify this is going to work or not.
Thank you.
Any other questions?
So when you try to learn, I might not have thought of this, but when you're trying to learn from the salient, learn the or cluster the actions, what exactly was your state space?
What was the state space? So you mean this case?
Yeah.
Right. So effectively, I mean, you have the initial location of the object, and you have some parameters for like whether you open and close your hand, and sort of the actual trajectory through there. And so the states. So afterwards, I think they might have actually looked at the change in state rather than the absolute state. But effectively, you get, for example, the position and the orientation of this object, right? So for the pushing, it's the fact that the object slides more to the right, for example, or for its carrying, it's moving up into the air, into the air.
So I guess it would like the actions would only apply to like this object specifically, and it doesn't seem to me that they're able to generalize to like different objects, right?
No. So this is a very, very simple developmental approach, right? So if you think about like a human child, right? For a human child, you would also, I mean, it would take years to sort of acquire some of these skills. We do have certain sort of benefits. So we do have like these reflexes. So if something touches the inside of our hand as a baby, we automatically close our hand. So that helps with the exploration. But this idea of so if you so this is going to give you very simple skills, but you would need to interact with a lot of different objects to start being able to identify like balls and cylinders roll, whereas cubes are only going to slide and tumble. Okay. All right.
I have a question.
Yep.
Sorry to go back to earlier slides. I didn't want to interrupt your explanation, but when you were talking about cutting the vegetables using your acoustic classifier, I wondered if you ever tried to combine that with a visual classifier to improve the results.
So we did not. So with the visual classifier, there's a lot of sort of occlusion that's going to happen, and things like the scraping. So initially we were mainly focused on the the detection of the different modes, not the different vegetables. And there is sort of the difference between this and this is very slight, and so it becomes fairly difficult to see it. If we had like a camera right next to it looking exactly at it, that might help, but we never tried that. We were fairly happy with the vibrations, and yeah.
Oh, on that, I think let's let Oliver finish the presentation first, and then we can do that.
To be honest, I'm absolutely happy to take questions. I mean, I have a whole bunch of extra slides, so I wasn't sure how quickly I was going to get through everything. The next part was going to be on sort of combining different sort of object-centric access controllers. So not looking at just sequential construction of skills, but also looking at parallel construction. But I'm more than happy. Like I feel like it'd be better use of time to maybe just discuss.
Okay,
or,
awesome.
answer questions.
Well, then let's great presentation. Well, I guess on that note, like when for the microphones, isn't that? I guess I was wondering like if the microphones are susceptible to like outside noise. So for example, if someone was talking during the experiment, would it affect the performance of content?
That's a great question. So for the scooping, let me find one. So originally we actually had two microphones. So we had the contact microphone in the back here, and then inside there we had sort of a lavalier microphone to sort of capture the environment. So our thinking was like, oh, exactly as you said, there's going to be background noise. We don't want to tell everyone in the lab to be quiet all the time. And so we thought like, oh, we'll just have this other microphone that picks up the background noise, and then we can do some kind of a source separation. But it turns out that actually not a lot of the vibrations get into the objects from the air. So I think it's sort of the transition from air to these sort of solid materials sort of attenuates a lot of those signals. So you get a lot of sort of removal of those signals from the environment fairly easily by using these sort of contact microphones, which are directly in contact with the objects. That said, there are also vibrations from inside the robot. So, you will get some of those influences. Sometimes you can sort of filter some of them out if they're at certain frequencies. Sometimes, you can add additional sort of damping sort of higher up on the wrist, for example. In some cases, you will get sort of these bands of vibrations, but, your classifier can effectively learn to ignore those because they're kind of very consistent across the different objects. So yeah, we also anticipated that to be a major error, but in practice, it hasn't been that big of a problem. And I think a lot of it is the fact that it attenuates a lot of the signal. We did have another experiment, so I don't have the slides for that, where we were sort of monitoring like a cooking process. So like we're currently looking at like frying eggs using visual and thermal cameras. We also tried a microphone there. Obviously, that's sort of picking up sort of the air, around it. We thought like, oh, maybe we can like hear sizzling. That one captured everything. So it's amazing how you can tell what people are doing in a kitchen just based on the audio. So the sound of vibration, the water flowing, stuff like that, or just footsteps walking around. So it turned out that was sort of, we had the opposite effect where it was capturing too much. So yeah, that's why I was thinking that vibrotactile sensing, because it's sort of contact based, it is a lot more local. It can go through tools, which is very useful. So knives, screwdrivers, scissors. But audio is going to give you that nice, all around sort of sensing because it's directly connected to the air.
For this particular application, what is the benefit of this over just keeping track of the weight directly?
So the idea was that we won't always be able to have the weight underneath there. We did sort of compare to a like a force torque sensor at the wrist, and it turns out that in this case we actually did get this 5 RMSE was actually better than using that force torque sensor. Again, I should mention the fact that it is a very specific type of motion. It's a specific scoop, so it wouldn't generalize between different scoops. But for sort of a niche application, this is a very cheap sort of sensor, and so that's definitely one of the benefits. So the contact microphones, they're a couple of dollars. We have a DAC which is quite expensive, but there's also ways of bringing that price down. So a low cost sensor that's easily deployed. That's kind of one of the reasons we're very interested in these microphones. I would also say that robustness is another factor. So a lot of tactile sensors, you're directly making contact with the sensor, which means there's going to be wear and tear over time. Whereas with this, where the back of it is being scooped into some coffee beans, but there's no scratches on the surface aren't going to actually cause a big problem for this.
I was actually wondering whether like the vibration response itself changes as the knife gets older. Like for a specific vegetable, the response might change as your knife gets older, and you might have to relearn everything.
I could definitely see that being the case. So yeah, like if you switch between different knives, I would expect there to be a shift. So this is definitely a cantilever. So if you take a smaller knife and just kind of ping it sort of from the side, you would expect some kind of higher vibrations. So yes, you would definitely need to sort of train across different kinds of knives in order to get that kind of robustness. Again, I think one